Why am I doing any of this? Sequences are useful for a variety of reasons. For starters, sequences help us understand repetitive processes, and some of those repetitive processes are useful if we're trying to compute something. Well, here's an example of such a process. I'll define a sequence recursively. X sub n plus 1 will be 1 over x sub n plus x sub n over 2. Maybe I'll start with the first term of this sequence as just being 1. Let's start with x sub 1 equals 1 and see what we get. Well, x sub 2 is 1 over x sub 1, which is 1, plus 1 over 2. That's 3 halves. You can also try to calculate x sub 3. I'd get that by taking 1 over x sub 2, so 1 over 3 halves, and adding that to 3 halves over 2. Now to do that calculation, well, I can write 1 over this fraction as 2/3, and instead of writing 3 over 2 divided by 2, I'll write that as 3/4. Now I want to put this over a common denominator of 12, so 2/3 is 8/12, and 3/4 is 9/12, so altogether x sub 3 is 17/12. We can compute more terms with the help of a computer. Here's the x sub 2 term that we just calculated. We can compute the next term. The x sub 3 term is 17/12. The x sub 4 term is 577 408ths. Here's the x sub 5 term. And what you'll notice is that these terms are getting closer and closer to the square root of 2. Even x sub 3, which is 17/12, is close to the square root of 2. Let's see how that works. So I want to try to convince you that 17/12 is approximately the square root of 2. Well, if I square both sides, what do I get? I'm getting that 17 squared divided by 12 squared should be approximately 2. And what's 17 squared? Well, 17 squared is 289, and 12 squared is 144. And is 289 over 144 close to 2? Yeah, because the numerator is just about twice the denominator. So one way to think about the square root of 2 is by thinking about this sequence. If you want to find a really good approximation to the square root of 2, all you've got to do is go far enough out in this sequence.